Okay, so let's continue with 15.4. We'll do a slightly shorter lecture. The last lecture was somewhat longer, so we'll do this one somewhat shorter. All we have to finish now from this section is integration in spherical coordinates. So what are spherical coordinates? Just to review, so this is when you what you do is if I have let's start with how the Cartesian coordinates look, right? And if I have some point over here, how do I get this in spherical? Well, I'm gonna look at the distance from the origin. I'm gonna call that rho. And if we project onto the xy plane, then this the angle that we make let's maybe start with here. So this angle is theta, and then we also need to know this angle, and that angle is phi, right? And again, as mentioned, when we first looked at spherical coordinates, it is not quite completely standardized. Different books, different people will use slightly different letters, and more confusingly, sometimes people swept these guys. It would be nice if they didn't, but they do. So you just have to deal with it. Well, we all have to deal with it. So, all right. So, how does this? What sort of equations we have? Well, this is where x is rho sine phi times cosine theta. That was really because rho sine phi is that's the x component. If we think of sorry, that's the rho sine phi is this distance over here, right? So this is really the x component in polar coordinates in the xy plane of this point over here, right? And similarly with y. And okay, so the z is slightly different. It's the rho cosine phi. All right. So, and you can sort of double check that these are correct. For example, just to make sure, if you want to remember if it's sine here or cosine here, well, it should be when let's say phi was 0, right? I should get that x and y are 0, and z is just equal to rho, and yeah, that's what I get. It's always good to sort of just mentally plug something in, just to see does that make sense? Does it correspond to the picture that you have? About these coordinates. So how do we integrate a function? We have some sort of a region that we describe in terms of rho, phi, and theta. For example, the easiest one is to describe is let's say the ball, the inside of the sphere, right, of some radius, because that's basically just the rho is less than or equal to that radius, right? So the unit ball, the what's the inside of the unit sphere, right? The the solid unit ball, well, that's exactly rho is less than or equal to 1, right? That's really easy to describe. By the way, here, this rho is always positive. Phi, well, it had better just go from 0 to pi, because you don't want to go sort of around twice. It's either you're on the sort of north pole at 0 and you're on the south pole when it's pi. And theta, again, some interval, interval of length 2 pi is good here, right? So to integrate, well, we need to figure out what that sort of basic volume element is, what that delta V is. And the delta V, if we, it's a little hard to draw, but let's try. So we're gonna have, if I put the origin over here, just to have a different picture. Basically, I start somewhere. If we move in terms of theta, right? Maybe it looks like this. If we move in terms of phi, it looks like this, right? And if we move in terms of rho, it looks like this. So basically, it looks sort of like this, right? Right, that's sort of the basic box. And again, it gets bigger as I go further away from the origin, right? Because this over here, that's rho. Okay, so now what are approximately the length of these sides? Let's just do the approximations immediately. Well, so the easiest one, going away from the origin, that is actually equal to, that's the change in rho. That's just delta rho. There's no problem in there. Now for let's say this the change in phi, right? Well, that's gonna be as you're basically just moving. Phi is just this angle, right? So it's really the length of, approximately the length of rho. So rho, how far we are, times delta phi, right? That one's easy. Now the hardest one, this guy, well, because here the angle is not this angle, it's the angle down here, right? When you sort of project these two lines out here, it's this angle over here. Okay, so we need to figure out what it's really has to do with this length rather than this length, right? So this length, well, that's we get that by sine rho times sine phi, right? So this is approximately rho times sine phi times delta theta, right? This length times this angle, right? All right, so that means that so that I have a little bit more space. It's approximately, not equal to, approximately. Well, it's let me just write them in some order, and then so delta rho times rho delta phi, right, times rho sine phi delta theta. Okay, well, that means that I can just rewrite this thing. Let me put I have rho sine phi. So I have rho squared sine phi, and then I just put the deltas in some order. Okay. So that means that my dv is going to be equal to rho squared sine phi d rho d phi d theta, or these can really then now go in any order, depending on how you describe your region. That will sort of tell you what order you need, right? So to integrate in spherical, you need to make this the dv. That's really that's the main thing, right? So let's do a couple of examples. So let's suppose that we have let's compute the volume of unit ball, right? That means that we want the volume of a ball of radius 1, right? Well, we could describe this by, as I said, rho is equal to 1, right? That describes this set. And so what this volume is, that's equal to just the triple integral. Let me call it, just so we have some name for it, b, right? And we're just integrating 1 with respect to the volume, right? And so let's write that as an iterated integral. We have 1, so let me just not put that in there at all. So I have rho squared sine phi d. Let's put these in. I can't really put them in any order here because it's this is sort of this is a spherical box. Before we said polar rectangles, so it would be a spherical box. It's just given by inequalities with constants. So d rho d theta d phi, right? And now let's figure out the limits over here. So rho goes, well, rho is always bigger than 0, bigger than or equal to 0, and it goes to 1, right? It's my rho. Theta. Well, theta really goes across everything, right? Means I have to go in all different theta, and the same thing for phi, right? So phi ranges between 0 and pi. Okay, so here we can actually separate this out because this is just a product of functions of the different variables, right? There's nothing in terms of theta, so we get this maybe the function 1, right? Then 0 to, let's do the rho guy, rho squared d rho, right? And then we have 0 to pi, right? Sine of phi d phi, right? And so we get, well, from this we get 2 pi, right? That was easy. From this we get, well, there's the antiderivative, right? Is rho cubed over 3, right? Evaluated from 0 to 1. So rho cubed over 3 is just 1/3, right? So there's a 1/3, and now over here we get this is well, the antiderivative of sine is minus cosine, right? And we get minus cosine at pi, which is, well, it's minus 1, right? let me maybe put that in here, right? Minus 1, this is minus cosine at pi, and then I have minus cosine at 1, so it's right, like this. In any case, it's 2, right? So I have 2 times 2 divided by 3, and I have a pi here, right? So this is 4/3 pi. Yeah, that's probably what you remember from high school geometry, right? Now, you could do this using Cartesian coordinates, but it would be really, really annoying to do this integral. Let's do one other small example today. So suppose we have let R be the ball, I wanted the half ball of radius 2, and the way that we'll define it is where x is bigger than 0 and x squared plus y squared plus z squared is less than or equal to 2 squared, right? That's the way that we describe it in Cartesian coordinates, let's say. And what we want to integrate is over r x squared plus y squared plus z squared, all with respect to the volume. Now, if you saw such a problem, you say, well, this looks really like something for spherical coordinates, right? Because what I have is, well, over here, the set itself is sort of nice in terms of spherical coordinates, right? And furthermore, if we have, if we look at the function that we're integrating, that's also nice in terms of the spherical coordinates. So this should become a much simpler if we do it in spherical coordinates, and it does. So how do we first describe R in terms of spherical coordinates? So R is the following in spherical coordinates. Well, how is x bigger than 0? X, y, z, right? I mean, it's basically this sort of it's a little hard to draw. It's this ball that it's just there's a half ball over here, right? Maybe you can sort of see it, right? But it's not the other side of it, right? Not for negative x. Well, what is how do we describe the x positive? Well, that's where theta is precisely the angle in the xy plane, where theta goes from minus pi over 2 to pi over 2. So this is where I want to use the range of thetas, not 0 to 2 pi. That's not convenient here, but a different range. And in this case, it's convenient to write it as minus pi over 2 to pi over 2. That's this inequality over here, right? That's what that means. And what does this mean? Well, this is where rho is less than or equal to 2, right? That's exactly what this inequality means. And it's everything inside, right? This is the distance from the origin squared, and we're saying that the distance from the origin squared is less than or equal to 2 squared, so the distance from the origin is less than 2. Okay, so now we can write down, let me say, that is equal to star, and star is equal to, well, we're gonna integrate to this iterated integral. This over here is rho squared. Then we have the dv, which is another rho squared, sine phi, and we have d. Let's put, again, it doesn't really matter. This is a spherical box. So let's do theta and phi. Doesn't really matter. So rho goes from 0 to 2. Theta goes from minus pi over 2 to pi over 2. And phi goes from, well, it still goes from 0 to pi, right? It's over all different phi's, right? I can go from, anywhere on this, from the North Pole all the way to the South Pole. Okay, again, this is just an iterated integral, right? So now you're experts at evaluating iterated integrals. Let me just do it, and again, it splits up nicely. It's just, I can do it as a product. Of course, you can't always do that, but in these simple ones, it works like that. It's not that really makes it all that much easier to evaluate. It makes it easier to write down, really. So I have the integral from 0 to pi of, let me write the phi first, phi, right, times, let's suppose that I have, now I have this guy, so minus pi over 2, d theta. There is nothing in terms of theta here, and I have rho to the fourth, so 2 rho to the fourth, d sorry, d rho. Okay, so now this is well, we've evaluated some of these before, right? So this one was 2. This one, well, this is pi, right? Because we're only going from minus pi over 2 to pi over 2, right? Integrating 1. Over here, we're gonna get rho to the rho to the fifth divided by 5 as the antiderivative, and we're evaluating at 2 and 0. So this is 2 to the fifth divided by 5. So, well, whatever that is, pi times 2 to the 6th over 5, whatever that is. All right. So that's how you integrate over spherical. It's basically, the main thing is to describe your region, and then write down the right iterated integral. You have to substitute the dv correctly, and then it's just evaluating iterated integral, just like any other integral, right? And there's nothing different in this computation.